All right, so now we're on 2003, question 1, and this is the one with the airplane, and it's accelerating uniformly from rest. And so we do have an acceleration, and it is from rest. And a physicist, passenger, holds a thin string of negligible mass, which she has tied her ring, which has a mass of m. She noticed that the plane accelerates down the runway, and the string makes an angle theta with the vertical as shown above. So first it wants us to draw a free body diagram. So of course we've got our mg and we've got our t, and that's it. And that's all the forces that you need to draw. So then the next part wants us to determine the minimum length of the runway needed. Basically, we want to know what is this change in x going to be. And so we have got the initial velocity equals 0 meters per second. We have got our final velocity equals 65 meters per second. We have got a time of 30 seconds. All right, so using this right here, we could use one of two equations, and both of the equations we're going to have two unknown variables. So I want to use the v squared equals v naught squared plus 2a change in x. And so we see that this v naught squared gets canceled because it's 0, so we get v squared equals 2a change in x. We're trying to get change in x by itself, so we divide both sides by 2a. And then so we get change in x equals this v squared all divided by this 2a. And so now we see they don't give us the acceleration. We need to first find that acceleration. So we can do that really quickly by saying v equals v naught plus at. Cross out your v naught, divide both sides by t. And so we get acceleration equals v divided by t, and so we get that 65 divided by 30, which is about 2.2 meters per second squared. Now we can plug all of our numbers in, so we get 65 squared divided by 2 times 2.2, and we end up with a change in x equaling about 975 meters. So that's about what you should get for that. All right, so then part C, it wants to know, determine the angle theta that the string makes with the vertical during the acceleration of the plane before it leaves the ground. So basically, we are looking for this theta right here, and so we don't really have a whole lot of room right here, so I'm going to do this on another sheet of paper. So the first thing that I'm going to do is I'm going to draw a free body diagram again. And so we've got the tension T, we've got our mg going down. And right now we are looking for this theta. All right. So what's causing this ring to go this direction? Well, you know that in a car, when you are slammed backwards, that means you are accelerating forward. So we have this acceleration going forward like that. And so what we're going to have to do is we are going to have to set up an equation. And so we see that this theta is due to this tension being in both the x and the y direction. So let's first look at our x direction. So F in the x direction, we said our acceleration is in this x direction. It's going to equal ma, which is going to equal this tension in the x direction, this t of x right here. And we see that this t of x has an opposite relationship with the angle, so you're going to say sine of theta equals this t of x all over this t. So we'll multiply that t by both sides, and we see that t of x is equal to t sine theta. And so then we get this ma equals t sine theta. But you guys, we see that we have got two unknowns. We've got this t and we've got that theta. So in order to figure out both those unknowns, we have to have two equations. So let's set up another equation. Some of the forces in the y direction, we see that there is no acceleration in the y. It's all in the x, so it's going to equal 0. And the forces that we have in the y direction are this tension in the y, t of y, minus that mg. We have to express this t of y in terms of t, and we see that this t of y has an adjacent relationship with the angle. So we're going to say cosine theta equals t of y divided by t, multiply both sides by t. So we end up with t of y equaling t cosine theta. And so this is going to be t cosine theta minus mg. And so these are our two equations. We have our 0 equals, or let's start with the first one. So we have our MA equals our T sine theta, and then we have this, this equation right here, which we can add the mg to both sides because it equals 0. So we're going to have this mg equals this T cosine theta. Now, because we only have one thing on each side, see how we just have this on one side and this on one side, we can do one of two things. The first thing we could do is we could use substitution. All right, we're trying to find this theta, so why don't we first solve for tension with using this equation right here. All right, and so let's divide both sides by cosine theta. So we end up with T equals mg divided by cosine theta. Now we can plug all this in for this tension right there. So we get MA equals this mg all over cosine theta times sine theta. And this becomes tangent theta. And so we get MA equals mg tangent theta. Well, we have m on both sides. We can cross that out. Divide both sides by g. And so we get tangent theta equals A all over G. We're trying to get theta by itself, so we're going to have to do the inverse tangent of both sides. So then we get theta equals inverse tan of A all over G. And so theta is going to equal tangent -1 times 2.2 divided by 10. And we end up with theta equaling about 12 degrees. Okay, if you got somewhere anything around in there, that sounds great. Now, there is another thing that we could have done with these two equations. So we started out with our MA equals T sine theta, and then MG equals T cosine theta. And because we only have one variable, one group of variables over here and one group of variables over here, we can just divide this equation. When we divide that equation, our m's go away. We get A all over G. Our t's go away. And then we see that sine over cosine is going to be tangent theta. So we end up with basically the same thing we did doing the substitution. And then so we end up with tan -1 equals A over G.